Alright, let's take the same sound example from earlier and modify it a bit. Now, we're not only going to change the frequency, but we're also going to change the amplitude or the volume of the sound. We will need a second vector of values for the amplitudes, and what we will do is we will play the same frequency for three different amplitudes and only then move on to the next frequency. So let's first create our amplitudes vector. So let's say that we want to hear the sound with an amplitude of 0.6, increment by 0.2 until we get to 1. So 0.6, 0.8, 0.6, 0.8 and 1. Now we need to add another loop, a nested loop. The first loop we will iterate over the frequencies and the second we will iterate over the amplitudes. That way we will be playing the same frequency for all amplitudes before moving on to the next frequency. If you use the amplitudes first and then the frequencies, you will hear all frequencies for the given amplitude and then you will move on to the next amplitude and start the frequencies from the beginning. In the end, with both approaches you will hear the exact same sounds, just in a different order. So the second loop will be for j equals from 1 to length of amplitude. We need an AND statement down here. Let's move everything a bit further. And here we need to recalculate the signal with the different amplitudes. So we are also going to give an index to our amplitude, which will be the J index. The I index will be switching on the frequencies, the J index will switch on the amplitudes. For a given frequency, we will first hear the three different amplitudes before moving on to the next frequency. So let's first make this with just two frequencies and three amplitudes. Let's run it and see if it's going to work. Well, it's working. And there it is, just as simple as that. We added a second loop, we added a second variable for our equation, and we modified it even more. With just two additional lines of code, we can now hear so many more variations of the same sound. We can even plot these signals and not only hear them, but see them. Let's use subplot for that purpose. First, to determine how many subplots we're going to have, we're going to take the length of the frequencies. Because if we have two frequencies, we have a variation for each frequency. All of the variations of the amplitude for the same frequency will go on the plot of the same frequency. So, length of frequencies 1, so we'll have all of the plots in one column. And to address each individual subplot, we are going to use the frequency index, the I index from the outer loop. Now, here we are going to plot, we're not going to plot the whole signal because we will not be able to see it because we have way too many points. So we'll plot only the first 1000 points. So we are going to take the time for x, 1 to 1000, and the signal 1 to 1000. Then we're going to hold on, here we need another bracket, and I'm also going to set a while limit from -1 to 1, because these are our minimum and maximum values for our signals, for our sounds. So let's run it. And there we have it. We have two subplots with different signals. You can clearly see that they have a different frequency, but the amplitude is the same. So we have different colors for the three different amplitudes that we have. Now, what we can do is we can modify our frequencies a bit. So let's say that we want 1000, 5000 and 15,000. All right, and we can run this. And we can clearly see, well, not that clearly on the last graph, because here the frequency is so big that we can't really see each individual signal. So with just a couple of lines of code, we generated so many different things. It's just amazing. This is what loops allow you to do. There we have it, even more. There we have it. We can clearly see it. We can do 100, we can do 500, and we can do 1000 and 1500. And now we will get 4 subplots, different subplots with the different frequencies, and if you want you can play a bit and customize them. Now, finally, if you want to save all of these new signals into a single matrix, you have to use a three-dimensional matrix. So far, we had our signals in a two-dimensional matrix. A given row of values was corresponding to a given frequency. So we had as many rows as we had frequencies to be calculated. But now we have that same two-dimensional matrix. The whole matrix is recalculated for each amplitude. So if we have 5 amplitudes, we have 5 different two-dimensional matrices. If we want to represent them in the same matrix, we have to make it a three-dimensional matrix. The first dimension represents the values of the signal itself. The second represents the frequencies, that is each row. And the third represents the amplitudes. So the same signal with the same frequencies for the different amplitudes. And to do this, first we have to add here our third dimension, which is amplitudes. And here in the signal section, we are going to say the current I row, the whole row, work on the J amplitude. So this is the third dimension for the matrices is basically, imagine it as a story building. Each of your two-dimensional matrices is simply a new floor for that building. The first floor is the all frequencies for amplitude 0.6. The second floor is for all frequencies with an amplitude of 0.8. The third floor is with amplitude 1.